The galaxy we inhabit, the one we call home, extends across a volume of space so immense that light itself requires approximately 100,000 years to traverse it from one edge to the other, and this fundamental measurement alone begins to suggest the scale of the structure we find ourselves embedded within. When we look up at the night sky from any sufficiently dark location on Earth, the band of diffuse light stretching across the heavens represents our edge-on view into this vast stellar system, a perspective that humans have contemplated for tens of thousands of years without understanding what they were actually seeing, and the journey from that ancient puzzlement to our current comprehension constitutes one of the most remarkable intellectual achievements in the history of science. The name itself carries etymological weight that connects us to ancient observations, as the term galaxy derives from the Greek word galaxias, meaning milky, which in turn comes from gala, the Greek word for milk, and this linguistic origin reflects the visual impression the phenomenon made on observers in the Mediterranean world, who saw in that celestial band a resemblance to spilled milk across the dark dome of the sky. The Romans similarly called it Via Lactea, the Milky Way, and this Latin terminology persisted into modern European languages, becoming the standard designation for our galactic home in English and many other languages. Other cultures developed their own interpretations and nomenclature, with various societies seeing in that band of light a celestial river, a path of spirits, or the backbone of the night. And these diverse interpretations remind us that the same astronomical phenomenon can generate radically different cultural meanings depending on the conceptual frameworks observers bring to their experience. The true nature of the Milky Way remained mysterious until surprisingly recently in human history, with serious scientific investigation of its structure only becoming possible in the 17th century following the development of the telescope. When Galileo Galilei turned his newly constructed telescope toward the Milky Way in 1609 and 1610, he made a discovery that fundamentally altered human understanding of that celestial band. Observing that what appeared to the unaided eye as a continuous glow actually resolved into countless individual stars, far too numerous to count and too faint to perceive individually without optical assistance. This observation, published in his work Sidereus Nuncius in 1610, represented one of the earliest applications of telescopic astronomy to cosmological questions, and it immediately suggested that the universe contained far more stars than anyone had previously imagined, a conclusion that carried profound implications for humanity's conception of its place in the cosmos. The question of whether the Milky Way constituted the entire universe, or merely one system among many, would take centuries to resolve, with serious debate continuing well into the 20th century. Thomas Wright of Durham proposed in 1750 that the Milky Way might be a flattened disk of stars with the Sun located within it, a suggestion that came remarkably close to the truth despite being based on limited observational evidence and considerable speculation. Immanuel Kant, the philosopher better known for his contributions to epistemology and ethics, extended Wright's ideas in 1755 by suggesting that the nebulous patches visible in the night sky might themselves be distant systems of stars similar to our own, what he called island universes, a term that captured the idea of isolated stellar systems scattered across the vastness of space. William Herschel, the German-born British astronomer who discovered Uranus, attempted the first systematic mapping of the Milky Way structure in the 1780s by counting stars in different directions and assuming that his telescope could penetrate to the edges of the stellar system, an assumption that proved incorrect but which nevertheless represented a pioneering effort to apply quantitative methods to galactic cartography. The fundamental problem facing early attempts to determine the structure and extent of the Milky Way involved the difficulty of measuring stellar distances, a challenge that plagued astronomy for centuries and that was only gradually overcome through the development of increasingly sophisticated techniques. The method of stellar parallax, which involves measuring the apparent shift in a star's position against the background of more distant stars as Earth orbits the Sun, had been proposed as early as the 16th century but proved extraordinarily difficult to apply in practice, because the shifts involved are so minuscule, requiring measurements of angular displacements smaller than 1 arcsecond for even the nearest stars. Friedrich Bessel finally succeeded in measuring the parallax of the star 61 Cygni in 1838, finding a value that placed the star approximately 11 light-years from Earth, and this measurement, along with nearly simultaneous successes by Thomas Henderson and Friedrich Struve for other stars, opened the door to determining distances to at least the nearest stellar neighbours. The parallax method remained limited to relatively nearby stars throughout the 19th and early 20th centuries. However, because the angular shifts become progressively smaller and harder to measure as stellar distances increase, and this limitation meant that the overall scale of the Milky Way remained uncertain for decades after the first successful parallax measurements. The breakthrough that finally allowed astronomers to probe the true dimensions of the Milky Way came through the work of Henrietta Swan Leavitt, an astronomer working at the Harvard College Observatory in the early 20th century, who discovered a relationship that would transform the field of galactic and extragalactic astronomy. Leavitt was studying a class of stars known as Cepheid variables, stars that pulsate in brightness with regular periods ranging from days to weeks, and she noticed that among Cepheids in the Small Magellanic Cloud, a satellite galaxy of the Milky Way visible from the southern hemisphere, there existed a correlation between the period of pulsation and the intrinsic luminosity of the star, with longer period Cepheids being intrinsically brighter than shorter period ones. This period luminosity relationship, published in 1912, provided a new method for determining cosmic distances, because if one could measure the period of a Cepheid variable, one could deduce its intrinsic brightness, and by comparing this intrinsic brightness to its apparent brightness as observed from Earth, one could calculate the distance to the star using the inverse square law that governs how light diminishes with distance. Harlow-Shapley applied Leavitt's period luminosity relationship to Cepheid variables in globular clusters, dense spherical collections of stars that orbit the Milky Way, and his results, published between 1918 and 1921, dramatically revised estimates of the galaxy's size while also displacing the Sun from the position near the galactic centre that most astronomers had previously assumed it occupied. Shapley found that the globular clusters were distributed asymmetrically across the sky, concentrated toward the constellation Sagittarius, and he correctly interpreted this asymmetry as evidence that the Sun was located far from the centre of the Milky Way, offset by a distance he estimated at approximately 50,000 light-years, a figure that was somewhat larger than modern estimates, but that correctly identified both the displacement and the direction of the galactic centre. Shapley's measurements also indicated that the Milky Way was far larger than previously thought, with a diameter he estimated at approximately 300,000 light-years, a figure that, while later revised downward, nevertheless represented a dramatic expansion of the known universe. The question of whether the spiral nebulae visible in telescopes represented objects within the Milky Way or independent galaxies beyond it remained contentious, even after Shapley's work, and this debate came to a head in the famous Great Debate of 1920 between Shapley and Heber Curtis at the Smithsonian Institution in Washington, D.C. Shapley argued that the Milky Way constituted essentially the entire universe, and that the spiral nebulae were relatively nearby objects within or around our galaxy, while Curtis contended that the spiral nebulae were independent island universes comparable in size to the Milky Way and located at enormous distances from it. The debate highlighted the genuine uncertainty that existed at the time and the limitations of the available observational evidence, with each side presenting arguments that seemed compelling within the framework of their assumptions, but that could not be definitively resolved without additional data. The resolution came through the work of Edwin Hubble, who in 1923 and 1924 used the newly completed 100-inch Hooker telescope at Mount Wilson Observatory in California to identify Cepheid variables in the Andromeda Nebula, a spiral nebula that had long been the subject of speculation regarding its nature and distance. By applying Leavitt's period luminosity relationship to these Cepheids, Hubble determined that Andromeda lay at a distance of approximately 900,000 light-years from Earth, a figure that, while later revised upward significantly, was nevertheless far beyond the boundaries of the Milky Way as Shapley had defined them. This measurement demonstrated conclusively that at least some spiral nebulae were indeed independent galaxies, vast stellar systems comparable to our own Milky Way and separated from it by intergalactic distances, and this conclusion fundamentally transformed human understanding of the cosmic landscape, revealing that the Milky Way was merely one galaxy among countless others distributed throughout a universe of previously unimagined extent. The structure of the Milky Way itself became a subject of intensive investigation throughout the 20th century, with astronomers gradually assembling a picture of our galaxy's architecture through observations at multiple wavelengths of the electromagnetic spectrum. The basic classification of the Milky Way as a spiral galaxy emerged from comparisons with external galaxies that could be viewed face-on, allowing their spiral arm patterns to be directly observed, and from radio observations that penetrated the dust clouds obscuring optical views of the galactic disk. The recognition that spiral arms represent density waves propagating through the galactic disk, rather than material features composed of the same stars over time, emerged from theoretical work in the 1960s by C.C. Lin and Frank Hsu, who proposed that spiral patterns are maintained by self-sustaining waves of gravitational compression that trigger star formation as gas clouds pass through the regions of enhanced density. The Milky Way is now understood to be a barred spiral galaxy, meaning that it possesses a central bar-shaped structure composed of stars orbiting in elongated paths, with spiral arms emerging from the ends of this bar and wrapping around the galactic disk. The recognition that the Milky Way contains a central bar came relatively late, with early evidence emerging in the 1990s from near-infrared observations that could penetrate the dust obscuring the galactic centre, and subsequent observations have confirmed and refined our understanding of this structure. The bar extends approximately 27,000 light-years in length and is oriented at an angle of roughly 45 degrees, relative to the line connecting the Sun to the galactic centre, a geometry that affects the orbits of stars in the inner regions of the galaxy, and that may play a role in channeling gas toward the central regions where new star formation can occur. The spiral arm structure of the Milky Way has proven difficult to map in detail because of our position within the galactic disk, which means that we must infer the three-dimensional arrangement of spiral features from observations made from a single vantage point embedded within the system we are trying to study. Current models identify four major spiral arms, named the Norma arm, the Scutum Centaurus arm, the Sagittarius arm and the Perseus arm, along with several smaller features including the Orion spur, also known as the local arm, which contains the Sun and represents a relatively minor structure connecting two of the major arms. The mapping of these features has relied on observations of young, hot stars and regions of ionized hydrogen gas called H2 regions, which serve as traces of recent star formation in the spiral arms, as well as radio observations of neutral hydrogen and carbon monoxide, which reveal the distribution of cold gas that follows the spiral pattern. The dimensions of the Milky Way have been refined through increasingly sophisticated observations and analysis over the past century, with current estimates placing the diameter of the stellar disk at approximately 100,000 to 200,000 light-years, depending on how the disk boundaries are defined and what stellar populations are included. The disk is relatively thin compared to its diameter, with a thickness of approximately 1,000 light-years in the vicinity of the Sun, though this thickness varies with distance from the galactic centre and with the age of the stellar population being considered, with older stars exhibiting a greater vertical distribution than younger ones. The central bulge, a roughly spheroidal concentration of stars at the heart of the galaxy, extends approximately 10,000 light-years from the centre, while a much more extended and diffuse stellar halo surrounds the disk and bulge, containing old stars and globular clusters distributed in a roughly spherical distribution that extends to at least 100,000 light-years from the galactic centre. The mass of the Milky Way represents one of the fundamental parameters of our galaxy, but determining this value has proven surprisingly challenging because much of the mass is invisible, consisting of dark matter that neither emits nor absorbs electromagnetic radiation, and that can only be detected through its gravitational effects. Current estimates place the total mass of the Milky Way at approximately 1 trillion solar masses, though uncertainties in this figure are substantial, with some analyses suggesting values as low as 500 billion solar masses and others as high as 2 trillion. Of this total mass, only a small fraction, perhaps 5 to 10%, consists of ordinary matter in the form of stars, gas, dust, and other visible components, while the vast majority is believed to be dark matter, distributed in an extended halo that encompasses and extends far beyond the visible components of the galaxy. the nature of dark matter remains one of the outstanding problems in astrophysics and particle physics, with numerous candidates having been proposed but none definitively identified despite decades of searching. The evidence for dark matter in the Milky Way and other galaxies comes primarily from observations of stellar and gas motions, which reveal gravitational forces too strong to be produced by the visible matter alone. In the Milky Way, the rotation curve, which describes how the orbital velocities of stars and gas clouds vary with distance from the galactic centre, remains approximately flat at large distances rather than declining as would be expected if the visible matter accounted for all the mass. And this flat rotation curve implies the presence of additional mass distributed in a way that extends well beyond the visible disk. Similar flat rotation curves have been observed in numerous other spiral galaxies, suggesting that dark matter halos are a general feature of galactic structure rather than something peculiar to the Milky Way. The stellar population of the Milky Way is estimated to contain between 100 billion and 400 billion stars, with the large uncertainty reflecting the difficulty of counting faint stars, particularly the numerous red dwarfs that constitute the majority of the stellar population by number, but that contribute relatively little to the galaxy's total luminosity. The census of stars in the Milky Way has been dramatically improved by space-based surveys, particularly the European Space Agency's Gaia mission, which was launched in 2013 and has been providing precise positions, distances and motions for nearly 2 billion stars, an achievement that has revolutionized our understanding of galactic structure and stellar populations. Before Gaia, estimates of the stellar population relied on statistical methods that involved observing relatively small samples of stars and extrapolating to the galaxy as a whole, an approach that was subject to significant systematic uncertainties. And while Gaia's sample still represents only a fraction of the total stellar population, its unprecedented precision has allowed for much more reliable estimates of the overall stellar content. The types of stars found in different parts of the Milky Way vary systematically in ways that reflect the galaxy's formation history and ongoing evolution. The thin disk, which contains the Sun and most of the galaxy's young and intermediate-age stars, is characterized by relatively high metallicity, meaning that its stars contain significant abundances of elements heavier than hydrogen and helium, which astronomers refer to collectively as metals, despite the fact that many of these elements, such as carbon and oxygen, are not metals in the chemical sense. The thick disk, a puffier component that extends above and below the thin disk, contains older stars with generally lower metallicities, suggesting that it formed earlier in the galaxy's history, when fewer generations of stars had enriched the interstellar medium with heavy elements. The bulge contains a mix of stellar populations, including both old, metal-poor stars and younger, metal-rich ones, reflecting a complex formation history that may have involved both the early collapse of gas and subsequent accretion of satellite systems. The stellar halo is dominated by old, metal-poor stars, including the globular clusters, which represent some of the oldest objects in the galaxy, with ages approaching 13 billion years. The interstellar medium of the Milky Way, the gas and dust that fills the space between stars, represents the raw material from which new stars form and the repository of heavy elements produced by previous generations of stellar nuclear synthesis. This medium is far from uniform, instead exhibiting structure across an enormous range of scales, from the cold, dense molecular clouds where stars form to the hot diffuse gas that fills much of the galactic volume. The total mass of interstellar gas in the Milky Way is estimated at approximately 10 to 15 billion solar masses, with roughly half in the form of atomic hydrogen, about 1/3 in molecular form primarily as hydrogen molecules, and the remainder in ionized phases. The distribution of this gas is concentrated in the galactic disk, with most of the molecular gas found within a few thousand light years of the galactic center in a structure known as the central molecular zone, while atomic and ionized gas extend throughout the disk and beyond. Dust, which consists of small solid particles composed primarily of silicates and carbonaceous materials, represents a small fraction of the interstellar medium by mass, perhaps 1% or less, but plays an enormously important role in galactic physics and in our ability to observe the galaxy. Dust particles scatter and absorb starlight, particularly at shorter wavelengths, causing distant stars to appear dimmer and redder than they would otherwise, an effect known as interstellar extinction that complicated early attempts to determine the structure and dimensions of the Milky Way. At the same time, dust particles emit thermal radiation in the infrared and far infrared, providing information about the temperature and distribution of the interstellar medium, and dust grains serve as sites for the formation of molecules, including the hydrogen molecules that are essential for star formation, by providing surfaces on which atoms can collide and combine. The process of star formation in the Milky Way continues at the present time, with new stars being born at a rate estimated at approximately 1 to 3 solar masses per year, meaning that the mass equivalent of 1 to 3 stars like our Sun is converted from interstellar gas into new stars annually. This rate has varied over the galaxy's history, with evidence suggesting that star formation was more vigorous in the past, particularly during the first few billion years after the galaxy's formation, and that it has generally declined over time as the reservoir of gas available for star formation has been progressively depleted. The current star formation rate is sufficient to maintain the galaxy's population of massive short-lived stars, which provide most of the ultraviolet radiation and inject energy into the interstellar medium through stellar winds and supernova explosions. But the overall trend points toward a future in which star formation gradually diminishes, and the galaxy becomes populated predominantly by long-lived low-mass stars. The regions where star formation currently occurs are concentrated along the spiral arms, where the compression associated with density waves triggers the collapse of molecular clouds into new stellar systems. The distribution of young stellar objects, including protostars, T-Tauri stars, and young stellar clusters, traces the spiral pattern, as do the H2 regions, ionized by radiation from hot, massive stars that have recently formed. The Orion Nebula, visible to the naked eye as a fuzzy patch in the sword of the constellation Orion, represents one of the nearest and best-studied sites of ongoing star formation, with new stars emerging from the dense molecular cloud behind the visible nebula at the present time. Other prominent star-forming regions in the Milky Way include the Carina Nebula, which hosts some of the most massive stars known, and the Sagittarius B2 complex near the galactic center, which is one of the most massive molecular clouds in the galaxy. The center of the Milky Way has been a subject of particular interest and intensive investigation, revealing an environment dramatically different from the relatively quiet solar neighborhood. At the very center of the galaxy lies a supermassive black hole, an object so compact that its gravitational field prevents even light from escaping, with a mass approximately 4 million times that of the Sun. This black hole, designated Sagittarius A, after the radio source associated with it, was first inferred from radio observations in the 1970s and has since been studied extensively through observations at radio, infrared, and X-ray wavelengths. The Nobel Prize in Physics for 2020 was awarded in part to Andrea Ghez and Reinhard Genzel for their work using infrared observations to track the orbits of stars in the immediate vicinity of the black hole, providing the most direct evidence for its existence and the most precise measurements of its mass. The stars orbiting closest to Sagittarius A move at tremendous velocities, with the closest approach of the star S2 bringing it within approximately 100 astronomical units of the black hole, about twice the distance from the Sun to Pluto, at which point it is travelling at approximately 3% of the speed of light. These observations have allowed astronomers to test predictions of general relativity in the strong gravitational field near the black hole, including the detection of gravitational redshift as light from S2 is stretched while climbing out of the black hole's gravitational well, and the measurement of relativistic precession as the orientation of S2's elliptical orbit slowly rotates around the black hole. In 2022, the Event Horizon Telescope, a global network of radio telescopes working together as a single Earth-sized instrument, released an image of Sagittarius A itself, showing the shadow of the black hole against the glowing ring of a hot gas swirling around it, providing the first direct visual evidence of the black hole at the center of our galaxy. The immediate environment of the supermassive black hole is remarkably dynamic, with stars forming, gas spiraling inward, and energetic processes producing radiation across the electromagnetic spectrum. The central molecular zone surrounding the galactic center contains an enormous mass of molecular gas, estimated at approximately 60 million solar masses, which represents a significant fraction of the total molecular gas in the galaxy, despite occupying a relatively small volume. Star formation in this region is suppressed compared to what would be expected given the high gas density, possibly due to the turbulent conditions and strong magnetic fields that characterize the galactic center environment. But when it does occur, it produces some of the most massive stellar clusters known, including the Arches cluster and the quintuplet cluster. The history of the Milky Way extends back approximately 13 billion years, to an era when the universe itself was less than a billion years old, and understanding this history requires integrating multiple lines of evidence from observations of our galaxy and comparisons with galaxies at various stages of evolution observed at cosmological distances. The formation of the Milky Way is believed to have begun with the collapse and cooling of gas within a dark matter halo that had grown through gravitational aggregation in the early universe, a process that led to the formation of the first generation of stars and the establishment of the basic structure that would evolve into the galaxy we observe today. The oldest stars in the Milky Way, including those found in globular clusters and the stellar halo, have ages that approach the age of the universe itself, indicating that star formation began very early in the galaxy's history. The subsequent evolution of the Milky Way involved the gradual accretion of additional matter, including both primordial gas that had not yet formed stars and smaller galaxies that were captured and absorbed through gravitational interactions. Evidence for this hierarchical assembly process comes from the detection of stellar streams, elongated structures of stars that trace the paths of disrupted satellite galaxies, as they were stretched and torn apart by the tidal forces of the Milky Way. The Sagittarius dwarf elliptical galaxy, currently located on the opposite side of the galactic center from the Sun, represents an ongoing merger event, with a stream of stars stripped from this dwarf galaxy wrapping around the Milky Way and providing a record of the orbit and disruption of the satellite. The Gaia mission has revealed numerous additional streams and substructures in the stellar halo, suggesting that the Milky Way has absorbed dozens of smaller galaxies over its history. One of the most significant merger events in the Milky Way's past occurred approximately 10 billion years ago, when a relatively large dwarf galaxy, now known as Gaia Enceladus, or the Gaia sausage, collided and merged with the proto-Milky Way. Evidence for this event comes from the identification of a distinct population of stars with unusual orbital properties, including highly eccentric orbits that carry them far from the galactic plane, combined with chemical abundances and ages that distinguish them from stars formed within the Milky Way itself. This merger is believed to have heated the pre-existing stellar disk, contributing to the formation of the thick disk component, and to have deposited a significant population of stars into the stellar halo. The discovery of the Gaia Enceladus merger, announced in 2018 based on data from the Gaia mission, represented a major advance in understanding the Milky Way's assembly history and demonstrated the power of combining precise astrometry with stellar chemistry to reconstruct events that occurred billions of years ago. The satellite galaxies of the Milky Way represent the most accessible examples of galactic companions and provide insights into the process of hierarchical structure formation that governs the growth of galaxies in the universe. The Milky Way is known to have approximately 60 satellite galaxies, ranging in size from the large and small Magellanic Clouds, which are visible to the naked eye from the southern hemisphere and contain billions of stars each, to the ultra-faint dwarf galaxies discovered in recent years that contain only a few thousand stars and are so diffuse that they were not recognized as distinct objects until the advent of modern wide-field surveys. The discovery of ultra-faint dwarf galaxies has accelerated dramatically since 2005, when the Sloan Digital Sky Survey began revealing these previously unknown objects, and the census of satellite galaxies continues to grow as new surveys probe fainter magnitudes and cover larger areas of the sky. The distribution of satellite galaxies around the Milky Way has raised intriguing questions about the nature of dark matter and the process of galaxy formation. The observed satellites appear to be arranged in a flattened disk-like configuration, rather than the roughly spherical distribution predicted by simulations of structure formation in the standard cosmological model, and this planar arrangement, known as the vast polar structure, has prompted debate about whether it represents a challenge to current theoretical understanding or a statistical fluctuation that falls within the expected range of variation. Additionally, the number of observed satellite galaxies has historically been lower than the number predicted by simulations, a discrepancy known as the missing satellites problem, though the discovery of ultra-faint dwarf galaxies and improved theoretical modelling have reduced the severity of this tension in recent years. The Magellanic Clouds deserve special attention as the most prominent satellite galaxies of the Milky Way, and as important laboratories for understanding stellar populations, star formation, and galactic interactions. The Large Magellanic Cloud, located approximately 160,000 light-years from Earth, is classified as an irregular galaxy, but shows evidence of a central bar structure and a single spiral arm, suggesting that it may have once been a more regular barred spiral, before being distorted by interactions with the Milky Way and the Small Magellanic Cloud. The Small Magellanic Cloud, located approximately 200,000 light-years away, is smaller and more irregular in structure, and together with the Large Magellanic Cloud and the Magellanic Stream, a filament of gas stretching across more than 100 degrees of the sky, forms a complex system whose evolution has been shaped by gravitational interactions among its components and with the Milky Way. The Magellanic Stream itself provides evidence for the ongoing interaction between the Magellanic Clouds and the Milky Way, as this ribbon of neutral hydrogen gas was stripped from the Magellanic System by gravitational tides and ram pressure as the clouds orbit through the hot gas of the Milky Way's halo. The stream extends approximately 200,000 light-years in length and contains a mass of gas estimated at several billion solar masses, representing a significant reservoir of material that may eventually fall onto the Milky Way and contribute to future star formation. Studies of the Magellanic System have also revealed the leading arm, a counterpart to the Magellanic Stream that extends in the direction of the cloud's motion, and that may represent gas stripped during an earlier passage. The place of the Milky Way within the larger cosmic structure represents another dimension of its significance, as our galaxy occupies a specific location within the hierarchy of clustering that characterizes the distribution of matter in the universe. The Milky Way is a member of the Local Group, a gravitationally bound collection of approximately 80 galaxies, spanning a volume roughly 10 million light-years in diameter, dominated by two major spiral galaxies, the Milky Way and the Andromeda Galaxy, with all other members being smaller satellite and dwarf galaxies associated with one of these two giants. The Andromeda Galaxy, also known as S31, is located approximately 2.5 million light-years from the Milky Way, and is slightly larger and more massive, making these two galaxies roughly comparable in overall significance within the Local Group. The Milky Way and Andromeda are approaching each other at approximately 110 kilometers per second, a relative velocity that will bring the two galaxies into a collision and eventual merger in approximately 4 to 5 billion years. Simulations of this future interaction suggest that the two galaxies will undergo multiple passages over a period of several billion years, during which their stars will be dramatically redistributed, their spiral structures will be disrupted and eventually destroyed, and the two systems will merge into a single, larger elliptical galaxy that has been informally dubbed Milkomeda or Milkdromeda. The individual stars within both galaxies are separated by such enormous distances that direct stellar collisions will be extremely rare during this merger, but the overall gravitational effects will fundamentally transform the stellar distributions of both systems, and the merger will likely trigger bursts of star formation as gas clouds collide and compress. The Local Group itself is part of a larger structure known as the Virgo supercluster, a collection of galaxy groups and clusters that extends across approximately 110 million light-years, and contains approximately 100 galaxy groups and clusters with a total mass estimated at 100 quadrillion solar masses. The Virgo supercluster is named after the Virgo cluster, the nearest major galaxy cluster and the gravitational center of the supercluster, located approximately 54 million light-years from the Milky Way and containing approximately 2,000 galaxies. More recently, astronomers have recognized that the Virgo supercluster is itself part of an even larger structure called Laniakea, a supercluster complex containing approximately 100,000 galaxies and spanning approximately 500 million light-years, within which the Milky Way occupies a relatively peripheral position. The motion of the Milky Way through this cosmic web of structure can be measured through observations of the cosmic microwave background radiation, the remnant glow of the hot, dense plasma that filled the universe approximately 400,000 years after the Big Bang. The cosmic microwave background appears slightly warmer in one direction and slightly cooler in the opposite direction due to the Doppler effect, reflecting the motion of the Milky Way relative to the reference frame in which the cosmic microwave background is uniform. This measurement indicates that the Milky Way is moving at approximately 600 kilometers per second toward a point in the direction of the constellation Centaurus, a motion that represents the combined gravitational pull of all the matter in the local universe, including the Virgo cluster, the Great Attractor, a concentration of mass in the direction of the Centaurus and Hydra constellations, and more distant structures. The cosmic environment of the Milky Way includes not only the gravitationally bound structures of which it is a part, but also the vast voids that occupy much of the volume of the universe. The local void, a region of space relatively devoid of galaxies, lies adjacent to the local group and extends approximately 150 million light-years, and the expansion of this void contributes to the motion of the local group through space. The interaction between the gravitational attraction of dense regions and the expansion away from underdense voids shapes the large-scale flow of galaxies through the universe, a phenomenon known as peculiar velocity that is superimposed on the overall expansion of the universe described by Hubble's law. The chemical evolution of the Milky Way represents a continuous process that has transformed the composition of the galaxy over its 13 billion-year history, as successive generations of stars have synthesized heavy elements in their interiors and returned them to the interstellar medium through stellar winds and supernova explosions. The very first stars to form in the universe, sometimes called population 3d stars, are believed to have contained essentially no elements heavier than helium, having formed from the pristine primordial gas produced in the Big Bang, which consisted of approximately 75% hydrogen and 25% helium by mass, with only trace amounts of lithium and beryllium. These first stars are predicted to have been massive and short-lived, ending their lives in supernova explosions that enriched their surroundings with the first heavy elements and seeded subsequent generations of star formation with the raw materials for more diverse chemistry. No population 3 stars have been definitively identified, likely because they were so massive that none have survived to the present day, but observations of extremely metal-poor stars in the Milky Way's halo provide glimpses of conditions in the early universe and constraints on the properties of the first stellar generations. These ancient metal-poor stars contain such low abundances of heavy elements that they must have formed from gas that had been enriched by only one or a few previous supernovae, and their chemical abundance patterns provide information about the nucleosynthetic processes that occurred in those early explosions. The most metal-poor stars known contain less than 1/10,000th of the iron abundance of the Sun, and their discovery requires careful searches using spectroscopic observations to identify candidates from among the much more common metal-rich stars. The enrichment of the Milky Way in heavy elements has proceeded through multiple channels, with different elements being produced predominantly through different processes. The alpha elements, which include oxygen, magnesium, silicon, sulfur, calcium, and titanium, are produced primarily in massive stars and dispersed through core collapse supernovae. The explosions that occur when massive stars exhaust their nuclear fuel and their cores collapse to form neutron stars or black holes. Iron and related elements are produced through both core collapse supernovae and type Ia supernovae, the thermonuclear explosions of white dwarf stars in binary systems, with the latter channel becoming increasingly important over time as the necessary white dwarf progenitors had time to form and evolve. The heaviest elements, including gold, platinum, and uranium, are produced through the rapid neutron capture process, or R process, which requires extremely neutron-rich environments and is believed to occur primarily in neutron star mergers and possibly in certain types of supernovae. The detection of gravitational waves from a neutron star merger in August 2017, designated GW1 and DW81, and the observation of its electromagnetic counterpart across the spectrum from gamma rays to radio waves, provided the first direct evidence for our process nucleosynthesis in neutron star mergers. The optical and infrared emission from this event, known as a kilonova, displayed the spectroscopic signatures of heavy elements freshly synthesized in the merger ejector, confirming long-standing theoretical predictions that neutron star mergers are A, and possibly the dominant site of R process element production. This observation connected gravitational wave astronomy with nuclear astrophysics and galactic chemical evolution, demonstrating how the heavy elements found on Earth and throughout the Milky Way were forged in cataclysmic cosmic events. The distribution of chemical abundances within the Milky Way reveals gradients and patterns that encode information about the galaxy's formation and evolutionary history. In general, stars closer to the galactic center tend to have higher metallicities than stars in the outer disk, reflecting the higher rates of star formation and chemical enrichment in the inner galaxy over cosmic time. This radial metallicity gradient has been measured using various tracers, including H2 regions, Cepheid variables, and open clusters, and its existence implies that the disk of the Milky Way did not form with uniform composition, but rather developed chemical inhomogeneities that have been partially but not completely erased by mixing over billions of years. Vertical gradients in metallicity are also observed, with stars farther from the galactic plane tending to have lower metallicities, consistent with the interpretation that the thick disk is older and formed from less enriched material than the thin disk. The concept of stellar populations, introduced by Walter Baird in the 1940s, provides a framework for understanding the relationship between stellar age, chemical composition, and spatial distribution within the Milky Way. Baird identified two distinct stellar populations in the Andromeda galaxy based on their observational properties. Population 1, consisting of young, metal-rich stars concentrated in the spiral arms and disk, and Population 2, consisting of old, metal-poor stars found in the bulge and halo. This classification scheme, though simplified, captures a fundamental pattern that has been elaborated and refined through subsequent research, and it highlights the connection between the temporal sequence of star formation in the galaxy and the present-day distribution of stellar properties. The age-metallicity-velocity relationship among disk stars illustrates how different stellar populations preserve information about the conditions at the time of their formation. Older disk stars tend to have lower metallicities, reflecting the less enriched state of the interstellar medium in the past, and they also tend to have higher velocity dispersions, meaning that their orbits are more eccentric and inclined relative to the circular orbits that characterize the youngest disk stars. This relationship can be understood as a consequence of dynamical heating, the gradual increase in orbital eccentricity and inclination caused by gravitational encounters with giant molecular clouds, spiral arms, and other perturbations, which accumulates over a star's lifetime and results in older stars having kinematically hotter distributions. The velocity dispersion of disk stars thus serves as a proxy for stellar age, a relationship that has been calibrated through studies of stellar populations with independently determined ages, and that has been used to constrain the history of the disk. The magnetic field of the Milky Way represents another fundamental property that affects numerous physical processes within the galaxy, from the propagation of cosmic rays to the dynamics of the interstellar medium and the alignment of dust grains. This magnetic field is generated and maintained by dynamo processes in the conducting plasma of the interstellar medium, with the differential rotation of the galactic disk, stretching and amplifying field lines while turbulent motions twist and reconnect them. The strength of the magnetic field varies throughout the galaxy, with typical values of a few microgauss in the disk and somewhat weaker fields in the halo, and the field configuration includes both large-scale ordered components that follow the spiral arm pattern and small-scale turbulent components that fluctuate on scales comparable to the sizes of molecular clouds. Observations of the galactic magnetic field employ multiple techniques, including measurements of the polarization of starlight by magnetically aligned dust grains, observations of the Faraday rotation experienced by polarized radio waves passing through magnetized plasma, and direct detection of the synchrotron radiation emitted by relativistic electrons spiraling around magnetic field lines. These observations have revealed that the large-scale magnetic field of the Milky Way has a predominantly toroidal configuration within the disk, meaning that field lines wrap around the galactic center in a pattern that roughly follows the spiral arms, while the field in the halo appears to have a significant poloidal component extending perpendicular to the disk. the total magnetic energy contained in the galactic magnetic field is comparable to the kinetic energy of interstellar turbulence and the thermal energy of the hot phase of the interstellar medium, indicating that magnetic forces play a dynamically significant role in the ecology of the galaxy. Cosmic rays, high-energy particles that pervade the Milky Way and constantly bombard Earth's atmosphere, represent another component of the galactic environment with important implications for astrophysics and potentially for the development of life. These particles consist primarily of protons and heavier atomic nuclei, with a small admixture of electrons and positrons, and they span an enormous range of energies from millions of electron volts to beyond 100 million trillion electron volts, more energy in a single subatomic particle than a baseball travelling at 90 miles per hour. The majority of cosmic rays observed at Earth are believed to originate within the Milky Way, accelerated to their high energies at supernova remnant shock fronts and other energetic sites, while the highest energy cosmic rays are thought to have extragalactic origins because their gyration radii in the galactic magnetic field exceed the dimensions of the galaxy itself. The confinement of cosmic rays within the Milky Way is accomplished by the galactic magnetic field, which causes charged particles to spiral around field lines and to scatter off irregularities in the field configuration, resulting in a diffusive propagation that keeps cosmic rays confined within the galaxy for millions of years before they escape into intergalactic space. This confinement time is much longer than the light crossing time of the galaxy, meaning that cosmic rays are stored within the galactic volume and that their energy density builds up to significant levels, approximately 1 electron volt per cubic centimetre, comparable to the energy densities of starlight, the galactic magnetic field and interstellar turbulence. The pressure exerted by cosmic rays contributes to the overall pressure balance in the interstellar medium and may play a role in driving galactic winds that carry gas out of the disk and into the halo. The interaction of cosmic rays with the interstellar medium produces gamma rays through various processes, including the decay of pions created when cosmic ray protons collide with interstellar gas nuclei, inverse Compton scattering of starlight photons by cosmic ray electrons, and the annihilation of positrons with electrons. Observations of the Milky Way at gamma-ray energies, conducted by space-based telescopes such as the Fermi Gamma Ray Space Telescope, have revealed diffuse emission from the galactic disk that traces the distribution of cosmic rays and interstellar matter, along with numerous point sources corresponding to pulsars, supernova remnants, and other sites of particle acceleration. An unexpected discovery from Fermi observations was the identification of large-scale structures known as the Fermi bubbles, two enormous lobes of gamma-ray emission, extending approximately 50,000 light-years above and below the galactic centre, whose origin remains debated but which may be related to past activity of the supermassive black hole or to intense star formation in the central regions. The question of how the Milky Way compares to other galaxies in the universe provides context for understanding whether our galactic home is typical or unusual in cosmic terms. In terms of fundamental properties such as mass, luminosity and size, the Milky Way falls within the range of values spanned by large spiral galaxies, neither at the extreme high end occupied by the most massive spirals, nor at the low end where dwarf galaxies reside. The Milky Way is often described as a fairly typical large spiral galaxy, though the meaning of typical in this context depends on the comparison sample, as most galaxies in the universe by number are actually dwarf galaxies much smaller and fainter than the Milky Way, making large spirals like ours relatively rare in an absolute sense, even as they account for a significant fraction of the stellar mass in the local universe. The barred spiral structure of the Milky Way is shared by approximately 2/3 of all spiral galaxies in the local universe, making this morphological type quite common, and the presence of a central bar may influence various aspects of galactic evolution, including the rate of gas transport toward the centre and the pattern of star formation within the disk. The grand design spiral pattern, exhibited by some galaxies, with two prominent, well-defined spiral arms emerging from a central bar or bulge, is not characteristic of the Milky Way, which instead displays a more flocculent arm structure, with multiple, less coherent arms and spurs. The exact classification of the Milky Way's spiral arm pattern remains somewhat uncertain due to our interior perspective, but it appears to fall between the extremes of grand design and flocculent spirals. The stellar mass of the Milky Way, estimated at approximately 50 to 70 billion solar masses, places it among the more massive spiral galaxies, but well below the most massive known examples, some of which contain stellar masses exceeding 1 trillion solar masses. The halo mass, which includes the dark matter component and extends far beyond the stellar disk, is considerably larger, with estimates ranging from 500 billion to 2 trillion solar masses as mentioned earlier, and this total mass determines the depth of the gravitational potential well within which the galaxy's stars and gas are confined. Comparisons with other galaxies suggest that the Milky Way falls near the peak of the galaxy's stellar mass function for spirals, meaning that spirals of similar mass to the Milky Way are roughly as common as spirals either more massive or less massive, placing our galaxy in a sense at the most typical mass for a large spiral. The star formation activity of the Milky Way, with its rate of 1 to 3 solar masses per year, is typical for spiral galaxies of its mass, neither elevated into the range of starburst galaxies that can form stars at rates of tens or hundreds of solar masses per year, nor suppressed to the negligible levels characteristic of elliptical galaxies and other quiescent systems. The gas fraction of the Milky Way, the ratio of gas mass to stellar mass, is approximately 10 to 15%, consistent with values observed in other late-type spiral galaxies, and implying that the Milky Way has sufficient fuel to continue forming stars at roughly its present rate for several billion years before gas depletion becomes limiting. The presence of significant ongoing star formation means that the Milky Way contains young, hot stars that provide ultraviolet radiation, H2, regions where gas is ionized by stellar radiation, and molecular clouds where the next generations of stars are gestating, all features that give the galaxy a dynamic and evolving character. The supermassive black hole at the centre of the Milky Way, with its mass of approximately 4 million solar masses, is relatively modest compared to the black holes found at the centres of many other galaxies, some of which exceed 10 billion solar masses. There exists a well-established correlation between the mass of a galaxy's central black hole and the mass or velocity dispersion of its bulge, known as the M-sigma relation, and the Milky Way's black hole mass falls close to the value predicted by this relation for a galaxy of its bulge properties, suggesting that whatever processes established this correlation operated in our galaxy as in others. The relatively low mass of Sagittarius A means that it is currently in a quiescent state, accreting matter at a very low rate and producing only modest luminosity compared to the active galactic nuclei and quasars powered by more rapidly accreting supermassive black holes in other galaxies. Evidence suggests that Sagittarius A youngs was more active in the past, with observations indicating that the supermassive black hole may have experienced outbursts of increased activity within the past few million years. The Fermi bubbles mentioned earlier, along with X-ray observations revealing hot gas and enhanced metallicity in the galactic center region, suggest that significant energy injection has occurred relatively recently in cosmic terms. The light echoes of past X-ray flares have been detected in molecular clouds near the galactic center, providing direct evidence that Sagittarius A was approximately 1 million times more luminous approximately 100 years ago than it is today, indicating that even on human timescales the activity of the central black hole can vary significantly. The question of whether the Milky Way is a typical environment for the development of life adds another dimension to considerations of our galaxy's properties. The habitability of a galaxy may depend on numerous factors, including the frequency of supernovae and gamma-ray bursts that could sterilize nearby planetary systems, the metallicity of the interstellar medium which affects the likelihood of forming rocky planets with appropriate compositions, and the dynamical stability of stellar orbits which determines how long a planetary system remains in a habitable location. The concept of a galactic habitable zone, analogous to the circumstellar habitable zone around individual stars, suggests that the conditions most favourable for life may be found in an annular region of the galactic disk, neither too close to the centre where stellar densities and supernova rates are high, nor too far from the centre where metallicities may be too low for rocky planet formation. The Sun's location within the Milky Way, approximately 26,000 light-years from the galactic centre and close to the midplane of the disk, places it within the proposed galactic habitable zone and in a region of relatively low stellar density where encounters with passing stars are infrequent. The Sun's orbit around the galactic centre is nearly circular, with an eccentricity of only about 5%, which minimises excursions toward the more crowded inner galaxy, or the metal-poor outer regions. Whether these properties are merely coincidental or reflect some deeper connection between galactic location and the emergence of complex life remains an open question, but they contribute to the characterization of Earth's cosmic environment as relatively benign by galactic standards. The rotation of the Milky Way provides a fundamental constraint on its dynamics and represents one of the most important measurable properties of the galaxy. The Sun completes one orbit around the galactic centre approximately every 225 to 250 million years, a period sometimes called a galactic year, and this timescale provides a useful reference for understanding galactic evolution, as the Milky Way has completed approximately 50 to 60 orbits since its formation. The orbital velocity of the Sun around the galactic centre is approximately 220 kilometers per second, and stars at similar distances from the centre have similar orbital velocities, reflecting the fact that the rotation curve of the Milky Way is approximately flat in the outer disk, rather than declining as would be expected for a centrally concentrated mass distribution following Kepler's laws. The differential rotation of the Milky Way, in which the angular velocity of orbiting material decreases with increasing distance from the centre, even though the linear velocity remains approximately constant, has important consequences for the structure and evolution of the galaxy. The spiral arm pattern is maintained despite differential rotation because the arms represent density waves rather than material structures, as mentioned earlier. But other features such as the winding of magnetic field lines and the shearing of molecular clouds are direct consequences of the differential rotation. The Oort constants, named after the Dutch astronomer Jan Oort who first derived them, parameterize the local rotation curve and differential rotation at the solar radius, and provide key constraints on the mass distribution within the disk. The vertical structure of the Milky Way, the distribution of stars and gas perpendicular to the galactic plane, reflects the balance between gravitational attraction toward the midplane and the random motions that support stellar populations against collapse. The thin disk has a scale height of approximately 300 parsecs, meaning that the stellar density decreases by a factor of about 2.7 for every 300 parsecs of elevation above or below the midplane, while the thick disk has a scale height of approximately 1000 parsecs, and the stellar halo has an even more extended distribution. The gas layer is thinner than the stellar disk in the solar neighbourhood, with a scale height of approximately 150 parsecs for the cold atomic and molecular gas, reflecting the lower velocity dispersion of the gas compared to the stars. The warp and flare of the galactic disk represent deviations from a simple flat structure that have been detected through observations of stellar and gas distributions at large distances from the galactic centre. Beyond approximately 40,000 light-years from the centre, the disk appears to bend upward on one side of the galaxy and downward on the other, with the amplitude of this warp increasing with radius, and simultaneously the disk becomes thicker at larger radii in a phenomenon known as flaring. The origin of the warp has been attributed to various causes, including the gravitational influence of the Magellanic Clouds, the accretion of intergalactic gas with angular momentum misaligned with the disk, or modes of oscillation inherent to the disk itself, and the relative contributions of these mechanisms remain a topic of ongoing investigation. The velocity structure of the Milky Way, as revealed by spectroscopic and astrometric observations, contains rich information about the galaxy's formation history, ongoing dynamical processes, and gravitational potential. Gaia's precise measurements of stellar positions and velocities have revealed numerous substructures in velocity space, including streams and overdensities that reflect the disruption of accreted satellite galaxies and the resonant effects of the bar and spiral arms. The phase spiral, a snail shell pattern, visible in plots of stellar position versus velocity perpendicular to the galactic plane, was discovered in Gaia data and indicates that the disk was recently perturbed by a gravitational disturbance, most likely an encounter with the Sagittarius dwarf galaxy, that set up vertical oscillations still visible in the stellar distribution approximately 500 million years later. The open clusters of the Milky Way, gravitationally bound collections of a few hundred to a few thousand stars that form together from a single molecular cloud, serve as important traces of the disk population and the history of star formation in the galaxy. Unlike the ancient globular clusters that populate the halo, open clusters are generally young, with ages ranging from a few million to a few billion years, and they are found almost exclusively within the galactic disk. Open clusters gradually disperse over time, as encounters with molecular clouds and other perturbations strip away their member stars, with typical dissolution timescales of a few 100 million years, meaning that only the youngest clusters remain well defined while older clusters have been spread throughout the field population. The Hyades and Pleiades, visible to the naked eye in the constellation Taurus, are among the nearest and best studied open clusters, while more distant clusters trace the spiral arm structure and provide samples of stellar populations at various ages and locations within the disk. The globular clusters of the Milky Way, by contrast, represent some of the oldest stellar systems in the galaxy and provide windows into conditions in the early universe. Approximately 150 globular clusters are known in the Milky Way, though additional faint clusters continue to be discovered, and these objects contain from tens of thousands to over 1 million stars packed into spherical distributions with typical radii of a few tens of light years. The ages of globular clusters, determined from the properties of their oldest stars, range from approximately 11 to 13 billion years, indicating formation very early in the history of the universe, and potentially before the Milky Way had fully assembled. The metallicity distribution of globular clusters is bimodal, with one population being relatively metal-poor and associated with the stellar halo, and another being more metal-rich and associated with the bulge, suggesting multiple epochs or modes of cluster formation. The stellar exotica of the Milky Way include objects that challenge our understanding of stellar evolution and that provide laboratories for extreme physics. Neutron stars, the collapsed cores of massive stars that have exploded as supernovae, pack approximately 1.4 solar masses into spheres only about 20 kilometers in diameter, creating densities exceeding that of atomic nuclei and magnetic fields billions of times stronger than any produced on Earth. Pulsars, rapidly rotating neutron stars that emit beams of radio waves from their magnetic poles, were first discovered in 1967 and now number in the thousands, with rotation periods ranging from milliseconds to seconds, and with observed slowdowns providing information about the energy loss from magnetic dipole radiation and particle emission. The most extreme pulsars, known as magnetas, possess magnetic field strengths up to 1 quadrillion Gauss, and produce occasional bursts of high-energy radiation that can be detected from across the galaxy. Black holes of stellar mass, the remnants of the most massive stars, are more difficult to detect than neutron stars because they do not emit electromagnetic radiation directly, but they reveal themselves through their gravitational effects on companion stars in binary systems and through the accretion of matter that produces X-ray emission. The first confirmed stellar mass black hole, Cygnus X1, was identified in the 1970s through observations of its X-ray emission and the spectroscopic orbit of its massive companion star, and numerous additional black hole binaries have been discovered since. The detection of gravitational waves from merging black holes by LIGO, beginning in 2015, has revealed a population of stellar mass black holes with masses significantly higher than those found in X-ray binaries, suggesting either different formation channels or selection effects in our detection methods. White dwarfs, the remnants of low and intermediate mass stars like the Sun, represent the final evolutionary state for the vast majority of stars in the Milky Way, and understanding their properties is essential for interpreting the stellar content of the galaxy. A white dwarf is typically about the size of Earth, but with a mass comparable to that of the Sun, resulting in densities of approximately 1 ton per cubic centimetre, and these objects cool gradually over billions of years as they radiate away their residual thermal energy without nuclear reactions to replace it. The white dwarf cooling sequence provides an independent method for determining the ages of stellar populations, as the luminosities and temperatures of the coolest white dwarfs in a system constrain the time elapsed since the first white dwarfs formed, and this technique has been applied to estimate the ages of the galactic disk and halo. The planetary systems of the Milky Way, now known to be extraordinarily common following decades of exoplanet discoveries, add another dimension to our understanding of the galaxy's contents and its potential for harbouring life. The first confirmed detection of an exoplanet around a Sun-like star was announced in 1995, when Michel Mayor and Didier Queloz reported the discovery of 51 Pegasi b, a gas giant orbiting its host star in only 4 days, and since then the catalogue of known exoplanets has grown to include more than 5,000 confirmed objects, with thousands of additional candidates awaiting verification. Statistical analyses of exoplanet detections, particularly from the Kepler Space Telescope, suggest that planets are abundant in the Milky Way, with most stars hosting at least one planet, and small, rocky planets being particularly common, implying that the total number of planets in the galaxy may exceed the number of stars by a significant factor. The diversity of planetary systems discovered has challenged theoretical models of planet formation that were developed based on the single example of our own solar system, revealing configurations including hot Jupiters on extremely close-in orbits, super-Earths and sub-Neptunes with no solar system analogues, planetary systems in resonant chains, and planets orbiting binary stars. This diversity suggests that the processes of planet formation and migration are more varied and complex than previously appreciated, and it raises questions about how common or rare the particular architecture of our own solar system might be. The search for potentially habitable exoplanets, particularly rocky planets in the habitable zones of their host stars where liquid water could exist on their surfaces, has become a major focus of exoplanet research, with several promising candidates identified, though none yet confirmed as truly Earth-like. The interstellar medium of the Milky Way, in addition to providing the raw material for star and planet formation, hosts a complex chemistry that has produced more than 200 different molecular species detected through their spectral signatures in radio and infrared observations. These molecules range from simple diatomics such as hydrogen, carbon monoxide and water, to complex organic compounds including amino acids, sugars, and precursors to the nucleotides that form DNA and RNA, suggesting that the chemical building blocks of life are produced abundantly in interstellar space before being incorporated into forming planetary systems. The field of astrochemistry has grown rapidly as observational capabilities have improved, with facilities such as the Atacama Large Millimeter Array enabling the detection of increasingly complex molecules in star-forming regions and protoplanetary disks. The hot phase of the interstellar medium, gas heated to temperatures of millions of degrees by supernova explosions and stellar winds, fills much of the volume of the Milky Way's disk and halo despite containing only a small fraction of the total interstellar mass. This hot gas, detected primarily through its X-ray emission and through absorption features in ultraviolet spectra, occupies the interiors of supernova remnants and stellar wind bubbles and connects with the hot gas of the galactic halo, potentially representing a medium through which energy and enriched material are transported from the disk into the halo. The cycle of energy and matter between the disk and halo, including galactic fountains in which gas is launched by supernova explosions and later falls back, and galactic winds in which gas escapes the galaxy entirely, represents an important aspect of galactic evolution that affects the rate of star formation and the chemical enrichment of the circumgalactic medium. The future evolution of the Milky Way, while uncertain in its details, can be projected in broad outline based on current understanding of galactic dynamics, stellar evolution, and cosmology. Over the next several billion years, the Milky Way will continue to form stars from its reservoir of gas, gradually depleting this reservoir as gas is locked up in long-lived low-mass stars and stellar remnants, with the star formation rate declining as the gas supply diminishes. The collision and eventual merger with the Andromeda galaxy, expected in approximately 4 to 5 billion years, will dramatically transform the structure of both galaxies, likely triggering a burst of star formation from shocked gas and ultimately producing an elliptical galaxy that will thereafter evolve passively as its stellar population ages. On still longer timescales, the stars of the merged system will gradually die, with the last red dwarf stars burning out perhaps 100 trillion years in the future, leaving behind a population of cooling white dwarfs, neutron stars, and black holes that will slowly fade into obscurity as the universe expands and cools. The accelerating expansion of the universe, driven by dark energy, will cause distant galaxies to recede beyond the observable horizon over the coming tens of billions of years, eventually leaving the local group as an isolated island in an otherwise empty observable universe. The Milky Way, merged by then with Andromeda and perhaps with other local group members, will become the only visible galaxy from the perspective of any inhabitants, and the cosmic microwave background will redshift to undetectable wavelengths, erasing the most direct evidence of the Big Bang. This long-term cosmological fate places the current era, with its rich population of observable galaxies and its accessible cosmic history, in a particular context, suggesting that while the universe has existed for approximately 14 billion years, the conditions that make it comprehensible through observation will not persist indefinitely. The Milky Way thus emerges from this extended examination as a complex, dynamic and evolving system whose properties encode information about physical processes ranging from cosmological structure formation to nuclear reactions in stellar interiors, from the behavior of matter at extreme densities in neutron stars to the delicate chemistry of interstellar molecular clouds. Our position within this system, while making certain observations more difficult, provides advantages as well, including the ability to study individual stars and stellar populations in detail, impossible for external galaxies, and the capacity to observe the three-dimensional distribution of matter through precise astrometric and spectroscopic measurements. The continuing development of observational capabilities, from space-based telescopes operating across the electromagnetic spectrum to gravitational wave detectors and neutrino observatories, promises to deepen our understanding of the Milky Way in coming decades, revealing structures and processes that remain hidden with current technology, and connecting our galactic home ever more completely to the broader fabric of astrophysical knowledge.